Hey guys, how are you all? Welcome back to the batch of excellence with Sagar Darvi, your chemistry teacher, where we learn organic chemistry with respect to boards, JEE as well as NEET. So guys, it's been several chapters we are meeting and we are learning organic chemistry since a long time now. You all are aware that in our course we are making sure that we are not just learning the syllabus of your boards but also putting an efforts to go beyond the line of boards and learning the course of competitive examination like JEE and NEET. With respect to that, we have come across some of the problem solving as well, just to give you an exposure that how exactly the questions have been asked in the competitive examination. Just like that, today we are starting with one more new chapter from organic chemistry, and one of the important chapter you will find at least one question on every alternate year at least, and the chapter is nothing but biomolecules. So guys, before we start, let me just brief you that this is a chapter which is basically a chapter from biochemistry, you can say, where you'll find some of the terminologies from biology would be used here. However, as far as our chemistry syllabus is concerned, we are going to only deal with the chemistry part of those biomolecules. So before we start, as usual, we'll first get introduced to what exactly we have to learn in our today's class. So everyone on your screen, we'll be first getting introduced to biomolecules, different types of biomolecules, in which we'll be starting with the first important biomolecule, that is carbohydrates. So we'll see the historical development of carbohydrates, how we used to earlier define carbohydrates and what is the modern way of defining the carbohydrates. Once that is done, we'll learn the classification of carbohydrates. We'll talk about important carbohydrate examples such as glucose molecule, because glucose is very commonly used carbohydrate in our daily lives. So we'll be talking about its structure, we'll talk about how it is being prepared and what are the different types of reactions of glucose. So reactions will include action of Tollens reagent, Fehling solution, Benedict solution. We'll also talk about oxidation using the reaction which is shown by this reagent. Same action is also shown by bromine water. Other than that, we'll also see oxidizing action of concentrated nitric acid, followed by some of the reduction reaction like reduction of D-glucose using sodium amalgam in water, and also red phosphorus and HI. These two reagents will be giving you different kind of reducing action on the carbohydrates. We'll then talk about reactions of the ammonia derivative, that is hydroxylamine. We'll also talk about addition of HCN. Finally, we'll see acetylation of glucose, and then another important reaction, that is reaction with phenylhydrazine. So guys, too many things to learn today, so let us not waste more time and get started with the first one. Let's get introduced to a chapter, that is biomolecule first. Well guys, when you talk about biomolecules, let's take it this way. Imagine if someone asks you, define growth, or what is growth of a body of a living organism. Let's talk about the growth of a human being. For a layman, we say growth is nothing but when you see a person was born, he was very small, probably weighing some 2.5 to 3.5 kg, that is an average weight. Probably you can say feet of a height, 1 feet. But when you see the same person 20 years down the line, you see that that person has grown up. And that growth you see in terms of the person then weighs after 20 years somewhere around 50 to 70 kg. You see that person is as tall as probably 5.5 to 6 feet. So this is what you call it as a growth of the body of that living organism. When we say that this growth has to take place, this growth is nothing but a cumulative effect of growth of the individual body parts, isn't it? When we say a person has grown up, meaning the individual body part seems to be grown up. Along with individual body parts, it is also the growth of organs, isn't it everyone? So when organ grows, individual body parts grows, and that eventually shows you the growth of a body. But if I ask you a simple question, what are those organs made up of? Organs are made up of tissues. Meaning when tissues will grow, organs will grow, and eventually we'll see the growth of body. But what are tissues made up of? Tissues are made up of cells. So cells has to grow. In order to tissues grow, which then eventually shows you growth of organs and then body parts and cumulatively the whole body. Whereas cells are made up of its small part that is called as cell organelles. So for cells to grow, the cell organelles has to grow. If cell organelles grows, cells grows, then tissues grows. That's how you see the growth in the organs, and that's how you see overall body growing. Now, eventually, if you think of what our cell organelles are made up of, you'll get an answer that cell organelles are made up of complex organic molecules, which is what we call it as biomolecules. So guys, eventually these are the biomolecules which are responsible for the growth of the body of living organism. So biomolecules responsible for the growth of cell organelles, cell organelles responsible for the growth of cells, cells shows you the growth of tissues, because of growth of tissues you see growth of organs and eventually growth of a body. And hence we say biomolecules are complex organic molecules responsible for the growth and the maintenance of living organisms. Well guys, this discussion was simply to make you understand that how important are biomolecules for the growth of a body of any living organism. So simply if someone asks you what are biomolecules, you can put it in this way. Biomolecules are complex organic molecules responsible for the growth and the maintenance of living organism. Now there are several type of important biomolecules exist for the existence of life cycles of a living organism, and those biomolecules includes carbohydrates, proteins, nucleic acid, etc. Now out of this, as far as our syllabus is concerned, we are first going to start with the first important biomolecule, that is nothing but carbohydrates. So guys, we're going to start with carbohydrates. Let us understand the carbohydrate first. Look, in old days, whenever we used to perform the structural determination of a compound, in fact even in these days we perform the similar process. So to find out the precise structure of a compound, what we used to do is we used to perform the elemental studies on that compound. Elemental studies includes what different types of elements are present in that molecule. So similarly, when we performed elemental study on carbohydrate, we realized that most of the carbohydrates were found to be containing these three elements: carbon, hydrogen, and oxygen, in a typical ratio of 1:2:1. Hence, if you write down this ratio C1H2O1, it appears as if C1, which even if you don't write, that is fine, H2, and O1, again if you don't write, that is still fine. This indicates that water molecule is in association with carbon atom. This indicates water molecule is in association with the carbon when you put this carbon, hydrogen, oxygen in a typical ratio in which they exist in nature as far as carbohydrates are concerned. But again, when you talk about CH2O, here this CH2O is what we call it as water molecule in association with carbon, as in we call it as hydrates of carbons. And guys, that's how you'll now realize the name carbohydrates came into picture, because it appears like water molecule is in association with carbon, meaning it is hydrates of carbon atom. Just to give you some example, well, we all are aware of a very common example, that is glucose. So if you talk about molecule of glucose, C6H12O6, that is nothing but glucose. You will find this glucose molecule also is existing in the form of hydrates of carbon. So I wrote it as CH2O, where how many are the number of carbon? 6, right? And how many are hydrogens? 12, oxygen 6, meaning I can multiply this by 6, and that's how you got C6H2O6. That indicates 6 water molecules are in association with 6 carbon atom, which means glucose is existing in the form of hydrates of carbon, so we can call it as carbohydrates. Similarly, if you talk about one more example, let's say if you talk about let's say sucrose. Sucrose is the compound with the formula C12H22. O11. That's sucrose, which you also call it as cane sugar or also known as table sugar. See student, even this sucrose I can put it in the form of hydrates of carbon. How can we put this? C12 and water molecule, if we multiply by 11, we'll certainly get C22O11, meaning sucrose is also another carbohydrate which we are able to put it in the form of hydrates of carbon. So yes, this is a carbohydrate. But when you observe these two examples, you will find the number of carbon and number of water molecule in glucose are identical. But number of carbon and number of water molecules in sucrose are not identical. Meaning not necessarily the number of carbon and number of water molecule has to be identical. And hence the same formula can be then simplified as CxH2O(Y). Hence, while defining carbohydrates, we used to define in old days as carbohydrates are complex organic molecules containing carbon, hydrogen, oxygen as an elements, and that can be represented in the form of hydrates of carbon, that is CxH2O(Y). Hence, we believe that if any compound is carbohydrate, it must be represented in the form of CxH2O(Y), or if any compound is existing in the form of CxH2O(Y), then that compound has to be carbohydrates. Yes, we believe it vice versa. If compound is carbohydrate, we should be able to put it in the form of CxH2O(Y). And if any unknown compound exists in the form of CxH2O(Y), that compound has to be carbohydrate. For example, glucose and fructose, we are able to put them in the form of CxH2O(Y), and therefore this compound certainly has to be carbohydrate. Well, we believe that this concept of carbohydrates or defining carbohydrates to be true for many years. But as the research went on, we started coming across some example which started challenging this way of defining carbohydrates. For example, suppose if I talk about molecules such as rhamnose, you'll see guys, everywhere when I'm using the term name of a sugar, the term is ending with OSE. OSE, basically it's a term that corresponds to sugar. Any compound which is sugar is always a carbohydrates. So rhamnose is the compound having a formula C6H12O6. Well, now tell me, are we in position to put this in the form of hydrates of carbon, CxH2O? Try and do that. For carbon, okay, you can multiply C6, that is the value of X. Now if you take H2O and if you multiply by 6, you'll get the number of hydrogen atom. Oh guys, little small change here, C6H12O5 it is. Yes, little correction here. Well, so in order to find out value of Y, imagine if you take the value of Y as 6, you'll get number of hydrogen 12, but number of oxygens we won't get 6 because it is O5. If I take value of Y as 5, the number of oxygen you will get as many are required, but we won't get the number of hydrogen as required, which means rhamnose, although being a carbohydrate, we are unable to put it in the form of hydrates of carbon. So not all carbohydrate will necessarily be represented in the form of hydrates of carbon. Let me just show you one more example. Other than rhamnose, well, there exists a sugar called as deoxyribose. I'm sure you all are aware of DNA, deoxyribose nucleic acid. Yes, nucleic acid is one of the important biomolecule. So sugar which is involved in that is deoxyribose. If I put this compound in its formula, it is C5. It's a pentose sugar, so C5, H10 and O4. See again, value of X can be taken as 5 to give you C5. H2O, if you take value of 5 as 5, you will get number of hydrogen, but number of oxygen will still remain 4. If you multiply, or if you multiply water by 4, that is taking the value of Y as 4, I'll get required number of oxygen, but 4 2s are 8 and we want 10 hydrogen atoms. So deoxyribose is another sugar or a carbohydrate which we are unable to put it in the form of hydrates of carbon. And that's why not always all the carbohydrates can be represented in the form of CxH2Y. And not only this, you will find there are several naturally occurring organic compounds which we can put it in the form of CxH2Y, but not really they are carbohydrates. For example, let's say if we have acetic acid. Well guys, acetic acid, a very common example, we are studying this since many chapters of organic chemistry. Precisely speaking, carboxylic acid, we have come across this. So acetic acid is the compound. We structurally represent it as CH3COOH. If you look at the molecular formula is C2H4O2. And now imagine if I want to put this in the form of hydrates of carbon, will we be able to do that? Yes, we can. How? Number of carbon, I took it 2. Water molecule, I am multiplying water molecule also by 2. So I got H4 and O2. So now acetic acid is the compound which we are able to put it in the form of hydrates of carbon. Does that mean that this is carbohydrates? Absolutely not. This is not a carbohydrate. That clearly indicates the old way of defining the carbohydrate is not always correct, because there exists some of the sugars, some of the carbohydrates which in spite of being sugar, we are unable to put them in the form of hydrates of carbon. And there are some non-carbohydrates which are not a carbohydrates but yet can be represented as hydrates of carbon. And that's why everyone, this is not the precise way of defining carbohydrates. So we will have to learn a modern way of defining carbohydrate. What exactly are carbohydrates? So now we are going to learn the modern way or modern definition of carbohydrate. To learn the modern definition of carbohydrate, what we will do is we will study some commonly known carbohydrate, like we'll study the structure of glucose, we'll study the structure of fructose, we will also study the reaction of sucrose. Now these three things are going to help us to define carbohydrate in real sense. So everyone, let's not look at the definition first. Like we said just now, we'll be first talking about structure of glucose and fructose. So let's say I'm talking about structure of D-glucose. D-glucose is represented by a molecular formula C6H12O6. So to get the structure of this glucose, we have got 6 carbon. Simple way of getting the structure is write down those 6 carbon in a straight chain carbon. So let's say if I'm putting that in the Fischer's formula, this is the first carbon, second, third, fourth, fifth, and this is sixth. So what we do is we make first carbon aldehydic. So first carbon we made it aldehyde. See, I'm putting that in the Fischer's projection. Last carbon I made it primary alcohol. And now as you move from bottom to top, you will see that the valencies of fifth, fourth, third and second carbon is yet to be satisfied. Those valencies I'm going to satisfy with the hydroxyl group in a sequence of RRLR. This is just a way to remember. RRLR stand for right, right, left, right. So as you move from the lowest chiral, see the last chiral, last carbon you have already satisfied its valency. Now from this carbon atom, fifth carbon, as you will move upward, you will put the group OH in this sequence. Right, right, left, right. Right, right, left, and right. And remaining valences we satisfy by hydrogen atom. And dear student, that's how we get the open chain structure of D-glucose. I repeat again. So the molecular formula for D-glucose is C6H12O6. What we did is, we wrote all the 6 carbon atom in a straight chain in the Fischer's projection. First carbon we made it aldehyde, last carbon we made it primary alcohol. Now from the second last carbon, from 5th carbon, moving upward, we are putting the OH group in the sequence of right, right, left, right. Remaining valences we satisfied by H, and that's how we got the open chain structure of D-glucose. Alright. Well, now why are we calling it as D? Although in stereochemistry and optical activity we have come across the designation called as capital D, L designation. Let me tell you, capital D, capital L designation has nothing to do with optical rotation, that is dextro or levo. There is no relation between this. So capital D and capital L designation stand for, if you look at the lowest chiral carbon atom of the molecule in the Fischer's projection, where is the OH group represented in carbohydrates? Like in this molecule, chiral carbon, we all know chiral is a tetrahedral carbon whose all the 4 valencies are satisfied by 4 different groups. So carbon number 2, 3, 4 and 5, all 4 are chiral carbon. The lowest chiral is this carbon, carbon number 5. And this lowest chiral carbon, the OH is present to the right in the Fischer's projection. Hence, such sugar is known as capital D sugar or capital D carbohydrates. Precisely speaking, this carbohydrate being glucose, I am calling it as D-glucose. Alright. Well, that was all about glucose. Similarly, let's talk about D-fructose. So let's say now we have got D-fructose. D-fructose also has the formula C6H12 and O6. To get the structure of D-fructose, again we'll be putting 6 carbon in a straight chain in the Fischer's projection. So let's say now we have, this is the first carbon which I'm making primary alcohol. This is second, third, fourth, fifth and sixth. Well guys, what we did, we put 6 carbon in a straight chain. First and the last carbon we made it primary alcohol. Second carbon I'm making it ketone. And then from bottom, that is from the lowest chiral carbon, meaning from the 5th carbon, we are going to move upward and again going to follow sequence right, right, left. So right, right and left. Remaining valencies we are satisfying with Hs. Now you may have a question, why are we putting this in a precise order of right, right, left or right, right, left, right in case of glucose? Well guys, if we convert the 3-dimensional structure of glucose into Fischer's projection, which is 2-dimensional representation of molecule, that is how the stereochemistry is represented. So based on stereochemistry, this orientation, based on the orientation in the stereochemistry of molecule, this is how the OH groups are put in the Fischer's projection, that is right, right, left, right. So we put it. Alright. Well, so guys, what we have got? We have got open chain structure of D-glucose and open chain structure of D-fructose. The whole idea is to be able to define the carbohydrates. Alright. Now see, what we did now. We tried and finding out the similarities in these two compounds. What are the similarities that we see in these two compounds? I can see glucose has a hydroxyl group, even fructose has a hydroxyl group. But they are not just one or two. There are many hydroxyl groups present. Hence, I will say the common thing in both of this compound is that they contain many hydroxy. Many hydroxy meaning I can call it as polyhydroxy. Polyhydroxy. That's the similarity. If I ask you what is the difference that you see, you will say in glucose we see functional group as aldehyde. In fructose, we see functional group as ketone. So if similarity is polyhydroxy, the differences are it may contain aldehyde or it may contain ketone. So polyhydroxy, aldehydes or ketones. Not to forget, whatever point we are jotting down are with respect to glucose and fructose. and both of them are carbohydrates. Hence, I can say carbohydrates are polyhydroxy aldehydes or ketones, right? Now, let's talk about one more example that we mentioned earlier is sucrose. Let's say I'm taking sucrose. Sucrose is the compound having formula C12H22O11. That is sucrose, also known as table sugar, also known as blood sugar. Now, the sucrose is subjected to process of hydrolysis in an acidic condition. Now see, we have got H2. If we add this 2 H's to sucrose, that 22 will become 24. Addition of 1 oxygen to O11 will make it O12. So we'll have C12H24O12. Now, because we are carrying out hydrolysis, this molecule will be broken into 2, each having formula C6H12O6. See, total is C12H24 and O12. You're breaking that into 2, each of the formula C6H12O6 plus C6H12O6, out of which one is D-glucose and other is D-fructose. Well, so what did we learn from this reaction? We know that glucose and fructose are carbohydrates and they are polyhydroxyaldehydes or ketone. Even sucrose is the example of carbohydrate. So can we say sucrose, which is a carbohydrate, upon hydrolysis again producing polyhydroxyaldehydes or ketone? Yes. So our carbohydrates could be polyhydroxyaldehydes or ketones or such a compounds which upon hydrolysis produces polyhydroxy aldehydes or ketones, right? Now guys, I want you to also observe when you look at these molecules, like I said, here the carbon number 2 is a chiral carbon, even this is a chiral carbon, third is a chiral, fourth is also a chiral carbon atom. Because of presence of 4 chiral carbon atom, N is equal to 4, the total number of optically active isomers will be 2 to the power n. Since the value of n is 4, 2 to the power 4. So 2 2s are 40, 2 2s are 4 2s are 16. Hold on. I'm sorry, 2 2s are 4, 4 2s are 8, 8 2s are 16. So the total number of optical isomers for this compound are going to be 16 isomers. Similarly, when you talk about fructose, how many chiral carbon do you see? 1, 2 and 3. 3 chiral carbon atom. So value of n is equal to 3, that is chiral carbon atom. So total number of optical isomer will be 2 to the power 3. So 2 2s are 4, 2s are 8. So the total number of optical isomers for fructose are going to be 8. That clearly indicates your carbohydrates other than polyhydroxyaldehydes or ketones or such a compound which upon hydrolysis produces polyhydroxyaldehydes or ketones, they are also going to be optically active. So we add that term as well. They are optically active. So guys, what are carbohydrates? Let's put these points together and define them. We will say carbohydrates are optically active polyhydroxyaldehydes or ketones or such a compounds which upon hydrolysis produces polyhydroxyaldehydes or ketones. And that's what you see over here at the top, which I asked you not to refer right in the beginning. So carbohydrates are optically active polyhydroxyaldehydes or ketones or such a compounds which upon hydrolysis produces polyhydroxyaldehydes or ketones. Well, dear students, what we have studied so far, let me just brief you that. We started our discussion with what are biomolecules. So you can say biomolecules are complex organic compounds which are responsible for the growth and the maintenance of the body of a living organism. Out of those biomolecules, we started with the first one, that is carbohydrates. We saw the old age concept or the earlier concept, you can say. According to the earlier concept, carbohydrates are complex organic molecules containing carbon, hydrogen, oxygen as an elements, and those has to be in the form of hydrates of carbon, which means they should be able to put it in the form of CxH2O. But not always all carbohydrates exist in the hydrates of carbon forms, and there are many non-carbohydrates which can be put it in the form of hydrates of carbon. So we learn the modern way of defining carbohydrates, that they are optically active polyhydroxyaldehydes or ketones or such a compound which upon hydrolysis produces polyhydroxyaldehydes or ketones. Alright guys, that was the brief introduction of carbohydrates. Now what we are going to learn is about classification of carbohydrates. So let us study classification of carbohydrates. Well guys, there are two ways by which we classify carbohydrates. First way, you can say on the basis of physical properties. Second, on the basis of chemical properties such as hydrolysis. Just give me a second. Okay. Yes, so we were talking about classification number one is on the basis of physical properties. So what we are going to learn, we will pick two examples of naturally occurring carbohydrates and we'll compare their physical properties. So what physical properties are we going to compare? We'll talk about taste of a compound, solubility in water, and nature. Nature as in whether it is amorphous or crystalline. Okay. So yes, so we decided to compare two naturally occurring carbohydrates such as cane sugar, the regular sugar that we eat, and potato, because we know that in potato there exists carbohydrate called as starch. Okay. Now guys, let's talk about sugar first. When you talk about sugar with respect to these properties, how does it taste? Sweet. Solubility, yes, sugar is soluble in water. Nature wise, we all know that it is certainly crystalline in nature. So we write it down. When you talk about sugar, it is sweet, it is soluble, and it is crystalline in nature. Isn't it, everyone? These all properties which we have jotted down, they all are corresponding to sugars. Now let's talk about the second compound, that is potato. Potato contains carbohydrate called as starch, right? Suppose if we extract starch from potato and we compare these three physical properties, taste wise, well, we all know that potato does not have any precise taste as such. So I will say it is tasteless. Tasteless. Solubility, if you take a starch and try to dissolve it in a water, it won't dissolve. So we say it is water insoluble. Insoluble. And you'll also observe that it is amorphous. Well guys, if you compare these three properties of starch with the properties of sugar, are they matching with the properties of sugar? Absolutely not. In fact, those are exactly opposite to that of properties of sugars. Hence, such compound like starch, which does not show properties similar to that of sugar, I will say starch is nothing but non-sugars. Hence, on the basis of physical property, we classify carbohydrates into two categories, sugars and non-sugars. What are sugars? Sweet, soluble, crystalline. What are non-sugars? Tasteless, insoluble, and amorphous in nature. So that was first classification on the basis of physical property. And now we are going to learn classification number 2, that is classification on the basis of chemical property, and the chemical reaction that we are going to deal with is a hydrolysis process. So what will we be doing is, we will be taking several carbohydrates and each one of those will be subjected to the process of hydrolysis, and we will observe the product and then classify accordingly. Okay. So guys, let us talk about classification number 2 on the basis of hydrolysis. You will see I have written 5 examples over here. Now each one of this example will subject it to the process of hydrolysis. To begin with, we'll talk about sucrose because this is the common example we studied just few minutes back. Sucrose is C12H22O11. Let's say I subjected this to the process of hydrolysis. Of course, in an acidic condition, I'm not mentioning the precise condition. So sucrose upon hydrolysis, C12H22. I've got 2 H's coming from water. If I add it here, it will become 24. 1 oxygen coming from water. If I add it here, it will become O12. And since it is hydrolysis, this oral formula, hold on everyone. Yes, so you will see the oral formula will be such where, hold on everyone. Hello, yes. So the oral formula upon addition of O1 will become O12, and since you're carrying out lysis of this formula will be broken into 2, each having formula C6H12O6 plus C6H12O6, out of which one is glucose and other is fructose. Alright, now suppose if I take any one of these two, let's say I've taken glucose, which I've taken it over here, and if I try to carry out similar hydrolysis process, like in case of sucrose, when we allowed sucrose to undergo hydrolysis, we got 2 units of carbohydrates, glucose and fructose. If I pick any one of this and subject it to process of hydrolysis, let's say if I subject it to process of hydrolysis, you will find they will not get further hydrolyzed. So I will say not hydrolyzed. Not hydrolyzed. Guys, what does that indicate? That indicate carbohydrates such as glucose or fructose, when taken alone individually, they are already a simplified form of carbohydrates that cannot be further hydrolyzed. Whereas sucrose is the type of carbohydrate which upon hydrolysis producing 2 units of carbohydrates, and those carbohydrates were such which cannot be further hydrolyzed. So those carbohydrates which cannot be further hydrolyzed, we call them as monosaccharides. Dear students, we call it as monosaccharide. So what are monosaccharides? The carbohydrates which are the simplified form or the simplest form of carbohydrates that cannot be further hydrolyzed. So what is sucrose? Sucrose is that carbohydrate which upon hydrolysis produces 2 units of monosaccharide. They are producing 2 units of monosaccharide. Those carbohydrate which upon hydrolysis produces 2 units of monosaccharide, we call it as disaccharide. What do we call it? Disaccharide. So yes, that's why sucrose is referred as disaccharide. Disaccharide. Now let's talk about raffinose. Raffinose is the compound or a carbohydrate having formula C18H32O16. Look, if I carry out hydrolysis of raffinose, which consumes 2 equivalent of water. So we have got total 4 hydrogens from water. If we add it to 32, it will become 36. 2 oxygen, if we add it to O16, will make it O18. So oral formula will be C18H36O18, and if you carry out hydrolysis, this will be broken into 3 units, each with the formula C6H12O6, whereas the first one is D-glucose. So we have got glucose. The second unit which we have got, again with the formula C6H12O6, which is nothing but fructose. And the third one which we are going to get here, C6H12O6, is nothing but galactose. So everyone tell me, raffinose is that carbohydrate which upon hydrolysis produced how many monosaccharides? Because if you pick any one of this individually, they are not going to get hydrolyzed. So such carbohydrates, raffinose, which upon hydrolysis produces 3 units of monosaccharide, we refer them as trisaccharides. So yes, raffinose is the example of trisaccharide. Similarly, stechiose, C24H42O21, is subjected to process of hydrolysis. Let's say it consumes 3 equivalent of water. Upon hydrolysis, 3 water meaning total 6 H's from water. If you add it here, it will become 48. 3 oxygen, if you add it here, it will become O24. Oral formula C24H48O24. Upon hydrolysis, you will be getting 4 units of monosaccharide. How? Let me show you that. The first one, C6H12O6, that is glucose. Along with this, we also get formation of C6H12O6, which is fructose, plus we get 2 units of C6H12O6, which is nothing but 2 units of galactose. So glucose, fructose plus 2 units of galactose. Such carbohydrate which upon hydrolysis produces 4 units of monosaccharides, we call it as tetrasaccharides. Hence stechiose is an example of tetrasaccharides. And finally, let's say if we have got molecules such as starch or cellulose. If we subject starch or cellulose to the process of hydrolysis, let's say I have taken n number of water molecule, ideally it should be n-1, but just by removing 1 water, it is not going to make much of a difference, so I'm just putting NH2O. Starch of the formula C6H10O5N, upon hydrolysis, it will produce n number of glucose molecules. So C6H12O6, this is nothing but many glucose molecules. So starch or cellulose for that matter are those types of carbohydrates which upon hydrolysis produces many units of monosaccharide. Such carbohydrate which produces many units of monosaccharides, we call it as polysaccharides. Polysaccharides. So everyone, you'll see here, there exist types of carbohydrate which are already simplified form that cannot be further hydrolyzed. We call it as monosaccharide. There are carbohydrate which upon hydrolysis produces 2 to 10 units. Example which we have seen are the ones which are producing 2 units, 3 units, 4 units. But collectively these are the types of carbohydrate which upon hydrolysis produces 2 to 10 units of monosaccharides. And such carbohydrate which produces 2 to 10 units of monosaccharide, collectively we call them as oligosaccharides. Oligosaccharides. Alright. So all these example which we have seen here, disaccharide, trisaccharide and tetrasaccharide, all these examples will belong to a category of oligosaccharide. Oligo meaning few, few meaning countable units. So if any carbohydrate upon hydrolysis it is going to produce countable units, we call it as oligosaccharide. And finally, there exists type of carbohydrates which upon hydrolysis produces many units of glucose, we call it as polysaccharide. Now see, if monosaccharide produced, the many number of monosaccharide units produced, if all of them are identical, you can call those polysaccharide as homopolysaccharide. And if many monosaccharides are obtained but mixture of monosaccharide, that is more than one type of monosaccharide if obtained, we call it as heteropolysaccharide. So polysaccharide could be of further two type, homopolysaccharide or heteropolysaccharides. So now we have got two classification. First one on the basis of taste, solubility in nature, that is sugars and non-sugars. Second on the basis of hydrolysis product, monosaccharide, oligosaccharide. Oligo further are of three type, di, tri, tetra, and then we have got polysaccharide. Now look, if you compare the properties of monosaccharide and oligosaccharide, example glucose, sucrose, raffinose, stachyose, if you compare the properties of this first four type that we have seen with the sugars, you will find the properties of these all monosaccharide and oligosaccharide are perfectly matching with the properties of sugars. For example, glucose is sweet, soluble, crystalline. If you talk about sucrose, in fact sugar, we started our discussion by taking example of sugar itself. So sucrose is also sweet, soluble, crystalline. That indicates monosaccharide and oligosaccharides are those carbohydrates which shows properties similar to that of sugars. Hence these first two classes, which two classes, monosaccharide and oligosaccharide, comes under sugars. So now we are merging these two classification, whereas the last one is polysaccharide. Polysaccharide meaning, see example, you have taken starch. Over there when we discuss about potato also contains starch which was tasteless, insoluble and amorphous. So polysaccharide will come under the category of non-sugars. Hence, by taking these two classifications together, now I will say carbohydrates are classified into two categories, sugars and non-sugars. Sugars are further two types. Which two types? Monosaccharides and oligosaccharides. While when you talk about monosaccharide, we saw monosaccharide two example, glucose and fructose, in which glucose contains a functional group aldehyde, fructose contains functional group ketones, and that's why monosaccharides can be further classified into two categories, that is aldoses and ketoses. So monosaccharides are of further two types, aldose and ketose, whereas oligosaccharides are of further three types. Oligosaccharide meaning those which produces 2 to 10 units of monosaccharide. In our syllabus we talk about only three classes of that: disaccharides, trisaccharide and tetrasaccharides. Disaccharide, trisaccharide, and tetrasaccharide. An example of each one of this we already know. Under aldoses we'll have glucose, for ketoses we'll have fructose, disaccharide sucrose, trisaccharide raffinose, tetrasaccharide stachyose. When it comes to non-sugars, non-sugars are nothing but polysaccharides. Non-sugars are hold on, nothing but polysaccharides. And like I said, depending upon what kind of hydrolysis product are we getting, as many monosaccharides will be getting. If all of them are identical, we call them as homopolysaccharide. And upon hydrolysis, if we get more than one type of monosaccharide, we call it as heteropolysaccharide. So polysaccharide is further of two types, that is homopolysaccharide and heteropolysaccharide. Heteropolysaccharide. Well, as far as examples are concerned, for homopolysaccharide, you can have example of starch or cellulose, because both of them are polysaccharide of glucose only. If you take a starch or a cellulose and carry out hydrolysis, you will get only units of glucose, nothing else. So those are homopolysaccharide. Whereas heteropolysaccharides upon hydrolysis gives you more than one type of monosaccharide. So gums is an example of heteropolysaccharides. So guys, that is the overall classification of carbohydrates. The details of this we have studied earlier in the previous slide. So we studied the introduction of biomolecules. We studied the introduction of carbohydrates. We saw according to modern way how are we supposed to define carbohydrates. In the process, we also learned drawing the open chain structure of D-glucose, open chain structure of D-fructose. We saw its characteristics feature, as in what groups are present in the molecule. We talked about its optical activity depending upon number of chiral carbon. Glucose will exist in 16 optically isomeric form. Fructose will exist in 8 optically active isomeric form. And then we also saw two classification based on physical property as sugars and non-sugar, based on hydrolysis process as monosaccharide, oligosaccharide and polysaccharides. When we mix these two classification, we get one final way of classifying carbohydrates into sugars, non-sugar. Sugar meaning mono oligosaccharide, non-sugar meaning polysaccharide, which is further of two type, homo and heteropolysaccharide. Whereas monosaccharides could be aldoses, ketoses, oligosaccharides are disaccharide, trisaccharide and tetrasaccharide. And in the previous slide, we saw examples of each one of this. Alright everyone, great. So that was all about classification of carbohydrates. And now we are going to discuss about a family of D sugars. Family of D sugars meaning what? Look, few minutes back we discussed about what exactly that term DL stand for. When it comes to small d and small l, is what you call it as the optical rotation, that is whether dextrorotatory compound or a levorotatory compound it is. But when it comes to capital D and capital L, it has nothing to do with the optical rotation of the sugars. Capital D and capital L is a relative configuration that talks about at the lowest chiral carbon atom in the Fischer's projection, whether OH is present to the right or whether OH is present to the left. In case of carbohydrate, in the Fischer's projection, at the lowest chiral carbon, if OH is present to the right, we call it as capital D sugar. And if it is present to the left, we call it as capital L sugar. So to understand, let us begin with the simplest D sugar. Now what you are going to see is a family of D sugar or the series of D sugars. And sugars are carbohydrates, so we have mentioned it as D series of carbohydrates. Let's talk about the first one, that is glyceraldehyde. So you'll see first carbon is aldehyde, last carbon primary alcohol, and at the second carbon I am putting OH to the right. So the second carbon, which itself is the lowest chiral carbon. See, the first carbon and third carbon is not the chiral carbon. The second carbon is the chiral carbon. At that chiral carbon, OH is present to the right. Because it is present to the right, I am calling it as D. And this compound is called as glyceraldehyde. So the name of molecule is D Glyceraldehyde. Diglyceraldehyde. Well, diglyceraldehyde is the example of how many carbon do you see? We see there are total 3 carbons. 3 carbons, so I'm using term tri. So it's a carbohydrate, meaning it's a sugar. So sugar containing 3 carbon is known as triose. So glyceraldehyde is example of triose. Okay. Now this glyceraldehyde will be considered as a parent of the entire D family. From this diglyceraldehyde, we will be preparing 2 more compounds. Now this is just the way of remembering all the members of D family. So you'll always consider diglyceraldehyde as your reference, and each time you go to the next member containing 1 extra carbon, you will have to add extra OH group at the newly formed chiral carbon. What I'm trying to tell you is, here diglyceraldehyde has 3 carbons. So from this I'm going to prepare 2 compound containing 4 carbon. You see 1, 2, 3, 4. How to do or how to prepare is, see, first carbon is going to remain aldehyde. Now when you make carbon from 3 to 4, you add 1 new carbon between the aldehyde group and the second carbon. So between these two you will be adding new carbon. So this is that new carbon, meaning third and fourth is nothing but this 2 carbon. So at fourth we have OH, at third we had OH to the right. So I'm keeping that same. And this is the new carbon you see whose valency are yet to be satisfied. Let's keep it this way only. So from this we have prepared 2. So the other one is also going to remain like that. First carbon is aldehyde, which is this. Now new carbon added just below aldehyde. So this is the new carbon. After that the 2 carbons are exactly the same which you see here, meaning OH to the right and CH2OH at the bottom carbon. Okay. So we have got 2 compounds derived from the parent, that is diglyceraldehyde, structurally, okay, not chemically. Now what we do is, the moment you get new compound with 1 new extra carbon atom, once you'll put OH to the right, once you'll put OH to the left. So in this case, let's say I put OH to the right, and here I am putting OH to the left. Remaining valencies we satisfy by H. That's how I got 2 more carbohydrates, 2 more sugars containing 4 carbon atom each. 1, 2, 3, 4. Since these are the sugar containing 4 carbon atom each, just like triose, I will now refer them as tetrose sugar. Okay. So the tetrose sugar that we have got, you'll see here, this is the compound containing 2 chiral carbon atom where OHs are to the right. So when both the OHs are to the right, we call it as D-erythrose. Alright. So D is again standing for, at the lowest chiral carbon OH is to the right. Obviously at the lowest chiral OH is going to remain right, because first, third and fourth carbon we kept it same as that of glyceraldehyde, and in this glyceraldehyde D was present to the right, so you call it as diglyceraldehyde, right? If this OH would have been to the left, you would have called it as capital L glyceraldehyde. So as of now it is D. So this, if the first one was D-erythrose, the second one is called as triose, D-triose. Alright guys, now this D-erythrose will give you 2 more sugars containing 1 extra carbon, meaning 5 carbon. D-triose will produce 2 more sugars containing 5 carbon atom. But again, when you come down from 4 to 5 carbon, the new carbon that you are adding has to be immediately after the function group aldehyde. So that's what we are going to do here. Look, let's talk about this. So first carbon you're going to keep constant, second one is going to be new for us. So first we kept constant aldehyde, second is the new carbon, so this is the new carbon here. Third, fourth, fifth will be this only, third, fourth, fifth. So OH, OH to the right, OH, OH and primary alcohol, remaining RHS. Here as well, the first one is aldehyde, This is the new carbon, and then OH, OH, and primary alcohol. Remaining valencies we satisfied with H. Now what are we going to do? The newly added chiral carbon, once you'll put OH to the right in the fissure, and once you'll put it to the left in the fissure. So once I put OH to the right, once I put it to the left, remaining valencies we are satisfying with H's. Alright. Now you will see this is the sugar containing how many carbon? This is the sugar containing 5 carbon. 1, 2, 3, 4, 5. And that's why this is called as pentose sugar. This is pentose sugar. First complete the structure, then we'll come to the naming part of these molecules. Now we'll be getting 2 more sugar from D3Os. So we'll be adding new carbon after aldehyde carbon. So first carbon you keep it aldehyde. This is the new carbon, leave it like that. And the next 3 carbon are left, right, right. Left, right, and CH2H is anyways you put it by the convention to the right. Remaining valencies are H's. Here as well, first carbon we make it aldehyde. Next is the newly added chiral carbon. Then left and right. And CH2OH. Remaining valencies with H. Okay. Now at the newly added chiral carbon, which is this, once you'll put OH to the right, and once you'll put it to the left. So here I'm putting it to the left. Remaining valency with H. So we got 2 more new sugars, each containing 5 carbon. So I got 2 more pentoses from triose, and earlier we have got 2 more pentoses from erythrose. Now what are their names? Well, so the first one is called as D-ribose. Yes, absolutely. Now I want you all to recall what is RNA. RNA is an abbreviation for, yes, what is RNA? Ribose nucleic acid. So this is the sugar which we use there, or it is rather it is present there. We don't use it. So ribose nucleic acid, this is the sugar which is present. So D-ribose. Next is D-arabinose. D-arabinose. Then next is D-xylose. D-xylose. And the next one is D-lyxose. L-Y-X-O-S-E. So what we have got here, from tetrose containing D-erythrose gave us 2 more new, D-threose gave us 2 more new pentoses. Name of each one is D-ribose, D-arabinose, D-xylose, and D-lyxose. Now you'll see each one of these 4 will produce 2 more by addition of new chiral carbon atom after the function of aldehyde. And that's how these 4 are going to give us 8 carbohydrates, each containing 6 carbon atom. Each containing 6 carbon atom, which means we will be now calling them all as what? Hexose. We'll be calling them as hexose. Now, everyone here. So what are we going to do? First aldehydic, and rest of the carbon we are going to keep same. So first aldehydic. This is the newly added chiral carbon. So rest all, starting with third carbon. OH. OH. OH we have kept it constant, and the bottom carbon is primary alcohol. The rest all are alcohols. Now here aldehydic, second carbon keeping same. OH, OH, and OH. Primary alcohol. H, H, and H. Now from D-ribose, the 2 new one which we have got, you will put once OH to the right. So here at the new chiral, I am putting OH to the right, here to the left. Rest is H. Now from D-arabinose, we are going to prepare 2 new. First carbon aldehyde. Second is the newly added chiral carbon, so rest you will keep same. Left, right, right. Okay. Left, right, right, and primary alcohol. Rest valency you are satisfying with H. Here also, other than newly added chiral, rest you will first arrange. So left, right, and right. Remaining are the valency satisfied by H's and primary alcohol. And now you will see you will be adding two new OHs. In the first structure you will put it to the right. So let's say I put it to the right, remaining is H. In the second structure you are putting it to the left and remaining is H. So now I want you to focus on this structure. Guys, what is this? 6 carbon carbohydrate with the OH group from the bottom, right, right, left, right. What is it? Right, right, left, right was the stereochemistry of D-glucose. So yes, this is what we have got as a D-glucose. We'll come back to this. Before which, let's complete the structure for the remaining hexoses as well. So now we are going to go a little quickly. We know how to do it. First carbon, we keep it same. Right, left, right. Okay. From third carbon. Right, left, right, primary alcohol. Remaining are H's. Here as well. Right, left, right, and primary alcohol. Okay. Here as well, first carbon aldehyde. Now see what we have had here. Left, left, right. Left, left, right, and primary alcohol. And the last example is also left, left, right after aldehyde. Leave the newly added chiral carbon left, left, and right. And now the two which are obtained from D-xylose, you'll add one OH to the right, one to the left. Remaining valencies with H's. Here OH added ones to the right, ones to the left, and we got series of carbohydrate, each containing 6 carbons, so we call them as hexoses. Now what is important are the names of this compound. Well, I'll first write it down. The first one is called as D-allose. D-allose. Next is D-altrose. And the next and the special ones, well guys, you all are aware that it is glucose. Right, 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 left, right. So that is D-glucose. I'm using different color for that so that we can easily identify it. Next is also important one, that is D-mannose. So all the important monosaccharide I'm writing with the green color so that you can identify them. Next is D-glucose. D-glucose. See, all of them we are calling it as D sugar because at the lowest chiral, that is at the second last carbon OH is present to the right. D-gulose. Little correction, guys. D-gulose. G-U-L-O-S-E. Next is D-idose. Idose, or you can call it as idose. Next is D-galactose. This is also very commonly used. You saw when we carried out hydrolysis of raffinose and stachyose, we got galactose. So this is the galactose. D-galactose. And the last one is talose, D-talose. So these are 8 sugar molecules that we have got, each containing 6 carbon atoms. Allose, altrose, glucose, mannose, glucose, idose or idose, galactose and D-talose. Well, to remember the names of this hexoses, probably you can remember with one sentence. The sentence is, all altrose gladly make gum in gallon tank. If you see the initials of this words that we are using, all, so we have got allose, altrose, so you have got ALT, altrose, gladly meaning you have got glucose, GL, make meaning MA, mannose, gum, that is GU, that is for glucose, gum in for idose, gallon, that is GAL for galactose, tank, that is TAL, TA for talose. All altrose gladly make gum in gallon tank. Well, again, let me tell you, not all you are ideally supposed to remember. When it comes to triose, tetrose and pentose, glyceraldehyde is pretty simple. Then erythrose and threose is a special naming system that you have also studied in stereochemistry, because erythrose, threose is the naming given to only those compound containing 2 chiral carbon atom. Such compound containing only 2 chiral carbon, when you put it in the Fischer's projection, and if identical groups are represented on the same side, so you call it as erythrose, like 2 OHs are on the same side, or you may say 2 H's are on the left hand side. But when those 2 identical groups are on the opposite side at the chiral center in the Fischer's projection, then you call it as threose. 5 carbons are ribose, arabinose, xylose and lixose. So I don't think so remembering name up to pentose is really that difficult, because they are quite simple. Yes, remembering the name of all hexoses become a little complicated, so for which I told you the statement, all altrose gladly make gum in gallon tank. Well, now what I want you guys to do is, I want you guys to compare 2 pair. Which 2 pair I'm talking about? I want you to compare the pair glucose and mannose. What are we doing here? Comparing. The first pair which we are comparing is D-glucose and D-mannose. See what I've told you? These are the common monosaccharide which you will see. Probably question can be asked upon. So you'll have to remember the structure. But again, remembering structure is not really that difficult. Why? Let's learn this concept first. If you see D-glucose and D-mannose, guys, look at the stereochemistry of OH group in the Fischer's projection. See, first is aldehyde. At the second carbon in glucose, OH is to the right. In mannose, OH to the left. That is at the second carbon. I'll just highlight that. We are talking about second carbon. But if you look at rest, all the carbon at third, OH is to the right. At third, OH is to the left. At fourth, OH is to the right. At fifth, OH is to the right. Meaning, other than orientation of OH group at the carbon number 2, at rest of the carbon, the orientation or the stereochemistry in this 2 molecule is exactly the same. Which means, now if I want to find out a relation between these 2, can I say these 2 are definitely non-mirror images of each other? Of course, because at one chiral carbon designation is different, and at rest designation is exactly the same. So we know what are diastereomers. Diastereomers are the one which shows similar or same configuration at least at one chiral carbon atom, and different configuration at least one of the chiral carbon atom. So these 2 are definitely non-mirror images. To compare whether they are diastereomers or not, we compare their mirror images. If they are not the mirror images, then you call them as diastereomers. Imagine if you have to write down IUPAC name of these 2 compound, IUPAC name will remain same. First carbon aldehyde, second, third, fourth, fifth, sixth contain hydroxy group, right? So this is going to be 2, 3, 4, 5, 6 hexahydroxy hexanal, a pentahydroxy hexanal. And the same IUPAC name remain even for the mannose. So these two are, everyone, these two are pair of stereoisomers which are not related to each other as a mirror images. So pair of stereoisomer of the same compound which are not related to each other as a mirror images, we call them as diastereomers. So these two are definitely diastereomer. But these are that kind of diastereomers whose configuration is different only at one chiral carbon atom out of many, isn't it? There is second carbon which is chiral, third is chiral, fourth is chiral, fifth is also chiral. But out of this many, the configuration is only differing at carbon number 2. So listen to me carefully. A pair of diastereomers which differ in their configuration only at one chiral carbon atom other than hemiacetylic carbon. Well, what is that hemiacetylic carbon? You haven't learned it yet. You will be learning it in the next class. But as of now, in the definition, we'll add it. When you learn something called as anomer, you'll come across this term. As of now, D-glucose and D-mannose are pair of diastereomers which are differing in their configuration only at one chiral carbon out of many. So such isomers are regarded as epimers. What do you call them? Epimers. So guys, you have studied term called as enantiomers, diastereomer, mesomer. Now the new term you have got is epimers. So D-glucose and D-mannose are epimers. And what type of epimers they are? They are C2 epimers. They are C2 epimers. Why they are C2 epimers? Because these two are diastereomers of the same compound differing in their configuration only at second carbon atom. At rest of the carbon, the configuration is exactly same. So we call them as epimers. Similarly, observe D-glucose and D-galactose. What are we comparing now? D-glucose and D-galactose. D-glucose and D-galactose. D-glucose and D-galactose. This is glucose and that is galactose. You will see at carbon number 2, OH is to the right, OH to the right, fine. At carbon number 3, OH is to the left. At carbon 3, OH is to the left. Still the configuration is same. But at carbon number 4 in glucose, OH is to the right. And here at 4, OH is to the left. Meaning configuration has differed at carbon number 4, C4. At 5th, OH is to the right. At 5th, OH is to the right. Meaning D-glucose and D-galactose are again pair of diastereomer, because if configuration is only differing at C4, they are not going to be mirror image of each other. So glucose and galactose are pair of diastereomers which are differing in their configuration at only one of the chiral carbon atom out of many. So even these two are the pair of epimers, and because configuration is different at C4, they are known as C4 epimers of each other. So guys, this is a new term called as epimers, which says when two molecules are diastereomeric to each other but differ in their configuration at any one of the chiral carbon atom other than anomeric carbon, meaning hemiacetylic carbon, you call them as epimer. Anomeric carbon, hemiacetylic carbon, do not worry as of now. When we'll see that term, you'll come across it. Alright guys, so now what I was talking about is you'll have to remember the structure of at least this three molecule, glucose, mannose and galactose. Is it difficult now? Acha, tell me, do you remember how to write down the structure of glucose? Yes, you do. 6 carbon in straight chain, first carbon aldehyde, bottom primary alcohol, then right, left and right. That is D-glucose. Once you know that the structure of D-glucose, then because you know D-mannose is a C2 epimer of D-glucose, can't we write structure of D-mannose? Yes, we can. Whatever is the structure of D-glucose, change the configuration only at C2. You'll get D-mannose. Because D-glucose and D-galactose are C4 epimers, whatever way you write structure for glucose, change configuration only at C4. You'll get the structure of D-galactose. That's how you can remember the structure of this two. Alright everyone. Great, so that was D family. of sugars. Now, whatever we define whatever we defined as epimers, we are just including the definition here. Pair of diastereomers which differ in their configuration at any one of the chiral carbon atom other than hemiacetylic, meaning anomeric carbon, you call it as epimers. Guys, one more question I would like to include here. Look, if you look at the structure of D-glucose, how have you derived it? You started from D-glyceraldehyde. The two compounds that you are getting, once you are putting OH to the right, in the other you are putting it to the left. Now imagine if I talk about L series, you don't need it, but suppose if you need L series, so what you will do? You will first prepare L-glyceraldehyde. What will be L-glyceraldehyde? At second carbon OH you will put it to the left. Now from that L-glyceraldehyde well, you will make two new compound of tetrose. First you will put OH to the left and then to right. Now what were you doing? From D-glyceraldehyde, new chiral carbon, in the first molecule you are putting OH to the right first and then to the left. But when you are preparing L series, you will take L-glyceraldehyde. In the first compound you will put OH to the left and then to the right. From this, when you will get 2, you will first put to the left, then to the right, so on and so forth. That's how you will come down to even L-glucose. So sometimes they ask question, how the structure of L-glucose looks like in the Fischer's projection. Let me tell you, if this is the D-glucose, and in a process the way I told you, if I try and derive the entire this tree for L family as well, you will find L-glucose will be the mirror image of D-glucose and not just the OH at the lowest chiral. No. Sometimes students feel that because D and L designation is distinguished on the basis of where the OH present at the lowest chiral carbon. So if this is D-glucose, to draw the structure of L-glucose, what do students do is only at the lowest chiral, meaning at fifth carbon, they put OH to the left. Rest they keep it as it is. That is not the correct capital L-glucose. So I'm telling you right now, if this is the structure of D-glucose, capital L-glucose is going to be a complete mirror image of D-glucose. Remember that. Okay, everyone. So yes, let's draw structure of D-glucose and glucose. D-glucose. And here we are going to write down L-glucose as well. First, second, third, fourth, fifth, and sixth. How do we remember? Right, left, and right. Remaining valency we satisfy with H. That's D-glucose. We have to get L-glucose. Like I said, it is always going to be mirror image of this. And this, if you want to get the structure, you can follow the same sequence the way we followed for D series, you can follow for L series. It's just that the first molecule you will get put OH to the left and then to the right. Okay. So as of now, I'm telling you a simple way. Directly remember, it's going to be a mirror image. First carbon aldehyde, second, third, fourth, fifth, and sixth. So if that was right, left, this will be left, right, and left. So that is nothing but L-glucose. Okay, in case if they ask you, so we have included that. So guys, we studied the D series of all the carbohydrate, which included triose, tetrose, pentose, and hexose. Now guys, that we have studied the open chain structure of glucose, we'll be now talking about methods of preparation of glucose and some chemical reactions of open chain structure of glucose. So to begin with, we will be learning methods of preparation of glucose. Well, this reaction, in fact, we have studied few minutes back while learning the classification of carbohydrates. I want you to just go through them. Okay. Well, so in the laboratory method of preparation of glucose, it can be prepared by the hydrolysis of sucrose. So we simply take sucrose, carry out hydrolysis. Upon hydrolysis, like we said, because sucrose is disaccharide, consumes one equivalent of water molecule in an acidic condition, that helps to break down the sucrose to give you one molecule of glucose and fructose, which can be then further separated by the process of crystallization. Secondly, as far as preparation of glucose industrial is concerned, where you want to prepare glucose in a large quantity, we prepare it from starch. So you can see we have got starch or from cellulose as well. When you carry out hydrolysis of starch or cellulose in an acidic condition at higher temperature and around 2 to 3 atmospheric pressure, the starch get hydrolyzed. Well, guys, just to remember the reaction, like I've been telling you, C6H10O5N. If you use excess of water, 2 H's, if you add it here, this will become O12, and addition of 1 O to O5 will make it O6. So C6H12O6. How many N number of those? Upon hydrolysis will produce many units of glucose. So this process will results in the formation of a large quantity of glucose. Hence we say preparation of glucose from starch is the industrial method for the preparation of glucose. So just two simple reactions that you will have to remember. Later we will see how this sucrose upon acid hydrolysis producing glucose and fructose is the process also known as inversion of sugar. So when we'll enter into the stereochemistry part of it, later we are going to see how this we call it as inversion of sugar. As of now, just remember sucrose upon hydrolysis producing glucose and fructose is also known as inversion of sugar, and the mixture of these two together, or the equimolar mixture of these two, is what you call it as invert sugar. As of now, let's proceed and talk about reactions of open chain structure of glucose. Well, everyone, whatever reactions we will be studying under this as a reactions of open chain glucose, ideally speaking, these reactions were performed to confirm the structure of a glucose. Like we know that glucose is the compound containing 6 carbon atom chain, first carbon aldehyde, bottom primary alcohol, then we have got right, left. So we have got total you can say 5 OHs, 1 aldehyde, 6 carbon. That all information we know. But this information was confirmed with the help of this kind of chemical reactions. So how this reaction helps us to testify the structure of open chain glucose, we are going to see that later. As of now, today when we are learning the reaction, we'll treat this reaction individually. So whatever reactions will be given to us, we'll use all the previous knowledge that we have studied in the chapter of alkanes, alcohols, and aldehydes and ketone, and we'll try to carry out the reactions. Okay. So to begin with, first set of reaction is oxidation reactions of glucose. There are two types of reagents that we're using: Tollens reagent, Fehling solution, Benedict solution, and also bromine water are the mild oxidizing agent. And other than that, we also have one strong oxidizing agent, that is concentrated nitric acid. So let us see here. Let's say we have glucose here. C double bond OH. Then we have got 4 secondary alcoholic group. So CHOH 4 times. I am writing them all together because this reagent does not hamper those secondary alcohol at all. So I am keeping them together. But at the bottom we have got primary alcohol as well, which I am highlighting. So that is D-glucose. Now we are allowing this D-glucose to react with different sets of reagents. So like I mentioned, the first one could be Tollens reagent. Or Fehling solution. or Benedict solution, or even bromine water. This all reagent being mild oxidizing agent, they only oxidizes aldehyde, or rather if you remember Toland's Fehling Benedict solution are the oxidizing agents, moderate oxidizing agent that helps oxidizing aldehyde to carboxylic acid. So this aldehyde will be oxidized to acid, the rest structure remain as it is, so the product obtained will be the first carbon which was aldehydic will now become carboxylic acid. Rest is CHOH 4 times and CH2 OHs. This product which is obtained is a carboxylic acid derivative of a glucose. You will see the aldehyde have been converted to acid. So this is the acidic form of a glucose, hence we call it as gluconic acid. So the product obtained is gluconic acid. So D-glucose upon reaction with moderate oxidizing agent oxidizes glucose into gluconic acid. On the other hand, if we treat that with a stronger oxidizing agent such as concentrated nitric acid being strong oxidizing agent, it does not just oxidizes the aldehyde into acid, but it will also oxidize the primary alcohol into carboxylic acid. Right, everyone? Strong oxidizing agents also has the ability to oxidize primary alcohol into acid. So first and the last carbon both will be oxidized to acid. So we'll be getting COOH, CHOH 4 times and COOH. So a dicarboxylic form of a glucose is known as saccaric acid. This is known as saccaric acid, sometimes also referred as glucaric acid. So everyone, glucose, open chain structure of glucose upon reaction with Toland's, Fehling, Benedict's or bromine water oxidizes only aldehyde to acid called gluconic acid. However, whereas oxidation with concentrated nitric acid will oxidize the aldehydic as well as primary alcoholic group into saccaric acid. Alright. Well, after oxidation, we'll now talk about reduction of glucose. So again, we are carrying out reduction using sodium amalgam in water and also by using red phosphorus NHI. So these two reagents are going to give you two different products altogether. So let's say we have glucose, first carbon aldehyde, CHOH 4 times, followed by CH2OH, this is D-glucose, and we are allowing this D-glucose to react with first reagent is sodium amalgam, in water, and the second one is red phosphorus plus HI. Well, everyone here, so sodium amalgam in water is a mild reducing agent which reduces the aldehyde group into alcohol. So you can see this is basically a metal acid combination. Metal acid combination, acid as in anything that is protic is acting like an acid here. So water is going to be a proton donor, so that will oxidize the carbonyl carbon atom. So to understand, Imagine if you just add H2 across carbon and oxygen, it will become CH single bond OH. So CH and one H is already there. So CH2 single bond OH. So the first aldehyde carbon will be converted to CH2OH. Then you already have CHOH 4 times secondary alcohol. And at the bottom, we again have primary alcohol. So this is nothing but hexahydric alcohol. So you'll see all the 6 carbon containing 1 OH each. Such hexahydric alcohol is also referred as sorbitol. So the product is sorbitol. Down here, glucose upon reaction with red phosphorus and HI. Well guys, when we study a chapter such as alkane, we have seen that alkane can be obtained by reducing several functional groups such as alkyl halides, alcohols, aldehydes, ketones, as well as carboxylic acid. All those functional groups can be straight away reduced by red phosphorus and HI into hydrocarbon without any change in the number of carbon atom. Again, mechanism of this reaction is out of scope for us. So we just remember that if any of those kind of functional groups, including alcohol, alkyl halide, aldehydes or ketones, if we allow it to react with red phosphorus and HI, it will convert that compound straight away into hydrocarbon, that is into alkane, without any change in the number of carbon. So in the context of glucose, how many carbon we have got? First, 4 secondary alcohol and 6. So we have got 6 carbon. First carbon is aldehyde, that can be reduced by red phosphorus HI. Second onwards up to 6 carbon, all are alcoholic, that can also be reduced by red phosphorus and HI. So all the 6 carbon atoms will be converted to corresponding hydrocarbon, that is alkane, which means the product is a normal chain alkane containing 6 carbon atoms, 1, 2, 3, 4, 5, 6. Hence the product is N-hexane. So glucose upon reaction with red phosphorus and HI will convert glucose into N-hexane. Alright. Well, next reaction with ammonia derivative called hydroxylamine and followed by HCN. Let's see both these reactions. So we have got aldehyde. C double bond O. Okay guys, hold on. Followed by a secondary alcoholic group. That's D-glucose. Let's say we are allowing it to react with hydroxylamine, NH2OH. Generally, these reactions of hydroxylamine with carbonyl compound is carried out in a weakly acidic medium which undergoes condensation. So carbonyl oxygen will be condensed with hydroxylamine to remove water molecule from here. So upon removal of water molecule, see what are we going to get. And this is CH double bond NOH carrying CH OH 4 times and CH2OH. So the aldehydic functional group have been now converted to CH double bond NOH. This functional group we call it as oxime. So this oxime is corresponding to starting compound glucose. Hence we call it as oxime of glucose, or also referred as glucoxime. Glucoxime. So reaction of hydroxylamine with glucose produces glucoxime. Now similar to that, if you look at HCN, guys, we have studied reaction of aldehydes and ketone with HCN. The same reaction will take place even with glucose, because in open chain glucose we have got free aldehydic group. So let's say we have aldehydic group. Hold on guys. HC double bond OCH OH 4 times and CH2 OH. We are treating this with HCN. Well, assuming this is nucleophilic addition reactions, let's say in basic conditions. So in basic condition, base whatever you're using will accept H plus, generating free cyanide ions. So this cyanide will attack at the deficient carbon, that is carbonyl carbon. This bond will break to make it O minus, which will then accept H plus from the second equivalent of HCN. So see, what is this going to be? CCN single bond OH, which means if we now represent the product formation, it will be HCCN single bond OH, right? This H was already existing. This became C single bond OH and attack of cyanide, followed by CH OH 4 times containing CH2OH. Such functional which is obtained containing hydroxyl and cyanide group due to addition of HCN to carbonyl carbon atom is what we referred as cyanohydrine. So yes, even this is a cyanohydrine of glucose. So cyanohydrine of glucose. Alright guys, so those were reactions of hydroxylamine and HCN with glucose. And now we'll be talking about acetylation. Well guys, when we studied in earlier reaction, in the earlier chapter when we talked about carboxylic acid, we saw a reaction called as acetylation, right? So let's say if we have compounds such as alcohol and we allow it to react with acid derivative. So when we talk about acetylation, earlier we have seen acetylation of alcohol, not carboxylic acids. Of course, acids also gives you acetylation reaction provided you treat with the alcoholic compound. So here we are talking about alcohol reacting with either acid or acid derivative. So let's say we have got some acid derivative here. And let us say this acetyl group is what we are going to introduce in alcohol by replacing this H. So this H has to be substituted by COCH3. So this H will be taken away with the remaining part, which is this. So let's say acetic acid is the byproduct which is removed. So this oxygen will be now connected to COCH3. So the product is going to be RO, and this RO is now connected to COCH3. Right? So if you see the overall change, you will find that the hydrogen of alcohol have been substituted by acetyl group, hence the process known as acetylation. Of course, with the elimination of byproduct acetic acid, this acetic acid is then consumed by using pyridine. So generally when you carry out acetylation, we use pyridine, that is base, in the reaction so that the byproduct which is obtained, that is carboxylic acid, will be absorbed or the neutralized by the base. So since this is a reaction of alcohol with the acid derivative, in a glucose, if we draw its structure, we have first carbon aldehyde, and second carbon onwards, all are what? Alcoholic OH group. So we have got 4 secondary alcoholic group, and the last one is also primary alcoholic group in the molecule of D-glucose. So now imagine if I have to subject this molecule to the process of acetylation. Since I have got 5 OH group, I'll need 5 equivalents of acetic anhydrides to carry out this reaction, right? In presence of pyridine. So total 5 acetic anhydrides. For our convenience, I'm writing like this. 4 I'm writing here together. CH3, C double bond O, O, C double bond O, CH3. This is 4 equivalent of acetic anhydride, which I've written against this 4 secondary OH group, and 1 I'm putting here. 1 equivalent of. So altogether 5 molecules. Alright everyone, and now carrying out reaction in presence of pyridine. So these acetyl groups are going to get substituted with the H's of alcoholic group. So we can show elimination this way. So byproduct will be 4 equivalents of CH3COOH. And from here, 1 more equivalent of acetic acid. So all the H's of alcoholic OH will be substituted by acetyl group. So the product obtained will be C double bond OH, CHO, and the group introduced is acetyl, that is C double bond O, CH3 4 times, and one more group introduced at C double bond O, CH3. So if you look at this group now, which is generated is CH3COO. It's a conjugate base of acetic acid. So this is the acetate group which is got attached. And how many such acetate do you see? 4 CH3CO and one more CH3CO. So 5 acetate, meaning penta-acetate groups have been introduced in the glucose. Hence we call it as glucose penta-acetate. Glucose penta-acetate. Alright everyone, glucose penta-acetate, that was acetylation of open chain glucose. Similar to this, even glucose reacts with phenylhydrazine when taken in excess to form bright crystalline derivatives of osazone, which you call it as osazone formation. So the next reaction of glucose is with phenylhydrazine. So you'll see phenylhydrazine in excess will be allowed to react with glucose to form a compound called as yellow-orange color crystalline compound called osazone. Well guys, we will not be discussing mechanism of this reaction, but I'll tell you simple way or simple trick to remember the product formation. Okay, so see what we are doing here. Let's say we have got first equivalent of phenylhydrazine reacting with glucose. So C double bond O, CHOH. I'm highlighting one of the OH, rest I'm keeping 3 together. So out of 4 secondary alcohol, I've kept 3 together, 1 I've highlighted. And down here, I have got CH2OH. That's D-glucose. Alright, and now we are allowing this to react with first equivalent of phenylhydrazine, NH2, NH, and pH. We'll mention it below this. First equivalent. So when you allow carbonyl compound to react with first equivalent of phenylhydrazine, it will undergo condensation with the carbonyl carbon. So we'll eliminate water from here. H2O when eliminated, carbon will be now doubly bonded connected to nitrogen. This is the way to remember, not the precise mechanism. So if you remove water from here, we will be getting CH double bond N NHPH. Followed by rest of the group as it is. That is CH OH and CHOH 4 times, 3 times here, followed by CH2OH. Okay, everyone. So if you try to recall what we had studied earlier in case of carbonyl compounds, if any aldehydes or ketones, if we condense that with phenylhydrazine, we used to get the product called as phenylhydrazone of aldehydes and ketones. Exactly in the same way, if this is glucose, if condensed with phenylhydrazine, the product obtained will be called as phenylhydrazone of glucose. So yes, product is phenylhydrazone of glucose. Phenylhydrazone of glucose. Okay, of course this is obtained upon condensation, so I'm writing elimination of water here. Now this phenylhydrazone which is obtained will be treated with the second equivalent of phenylhydrazine, NH2 NHPH. Look, second equivalent. Well, now consider as if this second equivalent of phenylhydrazine when reacts with this glucose phenylhydrazone or phenylhydrazone of glucose, it undergoes oxidation at carbon number 2. Let's assume it this way so that you can understand the reaction or you can remember it very well. So when you're carrying out oxidation at carbon number 2, oxidation could be removal of hydrogen. So imagine if you're removing these 2 hydrogens, this and this. So when these 2 H's will be removed, there will be formation of double bond between carbon and oxygen, so you'll get C double bond O. These 2 H's which you have removed, put them back here above nitrogen and break the bond. So the byproducts obtained would be ammonia and PHNH2 meaning aniline. And that's what actually you get as a product. So once you get phenylhydrazone of glucose, allow it to react with the second equivalent of phenylhydrazine. It will carry out oxidation at carbon number 2. So remove 2 H's, it will make it ketone and the byproduct will be ammonia and phenylhydrazine. So see, the product obtained will be CH double bond NHPH. Alright, this carbon I've kept it as it is. Second carbon will be now oxidized to ketone. So C double bond O and rest alcoholic group as it is. CH OH 3 times followed by CH2 OH. Okay, so this product which is obtained is known as glucosone, because you see now the functional we have got is ketone here. So it was glucose phenylhydrazone, you'll call it as glucosone phenylhydrazone. Glucosone phenylhydrazone. Glucosone phenylhydrazone, and along with this the byproduct which we have got is ammonia and aniline, which I'm writing it here, minus NH3 minus PH NH2. Okay, So guys, so far, first equivalent of phenylhydrazine upon reaction with D-glucose produces glucose phenylhydrazone or phenylhydrazone of glucose. Second equivalent of phenylhydrazine will oxidize carbon number 2 to make it glucosone phenylhydrazone. Now this glucosone phenylhydrazone will react with the third equivalent of phenylhydrazine, which we are writing it on the next slide. So what we had, CH double bond NNH pH. Carbon number 2 was oxidized to ketone. Next three secondary alkali group were as it is. The CHOH 3 times and CH2OH, right? This is what we call it as glucosone phenylhydrazone. I'll write it down again. Glucosone phenylhydrazone. And this was then further reacted with the third equivalent of phenylhydrazine. So let's say we have got NH2, NH, pH, which is third equivalent. The third equivalent of phenylhydrazine react with glucosone phenylhydrazone, which further undergoes condensation. So elimination of water will give you C double bond NNHPH. Upon elimination of water, see what we have got. First carbon was as it is CH double bond N NH pH followed by, now again we have got the similar kind of structure, C double bond N NHPH, right? C double bond N NH pH and rest of the structure as it is, which is CH OH 3 times followed by CH2OH. This product which is obtained is what you call it as oxazone of a glucose. That's the final product. So you will see this is oxazone of glucose, which can simply be also called as glucosazone. And this product is obtained as a yellow-orange color crystalline compound. So as soon as this is formed, it crystallizes out because you will see the product obtained is extremely stable due to extended conjugation. In this phenyl ring, you'll have 3 pi bonds in conjugation, which is in conjugation with this lone pair, pi, alternate lone, alternate pi, alternate lone, alternate 3 pi bonds further. So because of so much of extended conjugation, this molecule is extremely stable and hence crystallizes out. If we talk about the overall reaction here, we can say glucose react with 3 equivalents of phenylhydrazine produces yellow-orange crystalline compound called as glucosazone or oxazone of glucose. So guys, those were reactions of open chain structure of glucose. Well, now let me brief you something which we'll be again seeing in the next class. However, why were this reaction performed? Like I said, these reactions were performed for the structural determination, or you can say confirmation of the glucose. Now, how this reaction helps us to confirm the structure of glucose? See, when we see the structure of glucose, how do we write it? We write 6 carbon in straight chain. First carbon, we make it aldehyde. Bottom carbon, we make it primary alcohol. And then we have got 4 more secondary alcohol group in between. Now, how to ensure that glucose has only 6 carbon atom? So imagine if we got a glucose compound, and if that glucose molecule was subjected to the reduction process using red phosphorus and HI, we got N-hexane. So red phosphorus and HI is that reducing agent, reduces many of the functions straight away to hydrocarbon without any change in the number of carbon atom. So when we reduced with red phosphorus and HI to give us N-hexane, that indicates glucose must be containing 6 carbon atom. So reduction with red phosphorus and HI ensured that the glucose contains 6 carbon. But just 6 carbon does not indicate its other structural feature, as in what kind of functional groups are present. So what we did, we allowed glucose to react with acetic anhydride. The product which was obtained was glucose pentaacetate. When acid derivative is treated with some compound which gives you acetylated product, meaning that other compound must contain alcoholic OH group. But since we got pentaacetate, this reaction ensured that in that 6 carbon chain of a glucose, there are 5 alcoholic OH group present. Now, when we allowed this compound to react with, if you take glucose, and if we allow to react with compounds such as hydroxylamine or HCN, we got condensation product. We got oxime of glucose, we got cyanohydrine of glucose. That again ensure other than 5 alcoholic OH, we have got 1 carbonyl group also present. But carbonyl group does not indicate whether aldehydes or ketone. So we carried out, let's say, third reaction. We allowed that glucose to react with Tollens reagent or Fehling solution or Benedict solution. And if we get silver mirror, silver precipitate or red precipitate of Cu2, that indicates that carbonyl carbon is not ketone, it's aldehyde. Because Tollens reagent can only oxidize, or Tollens reagent can only be reduced when the compound contains aldehyde. So see, by this set of reactions, what all conclusion we got? We got to know that glucose contains 6 carbon from red phosphorus and HI. From acetylation, we got to know that there are 5 alcoholic group. From hydroxylamine and HCN, we got to know that there is carbonyl carbon. And with Tollens reagent test, we got to know that carbonyl carbon is aldehydic. So far, the structural information that we have is glucose contain, 1 molecule of glucose will contain 6 carbon atom, 1 aldehydic and 5 alcoholic OH groups. So guys, this kind of reaction helps us eventually to determine the structure of glucose, and that was the whole purpose of carrying out this reaction. However, when we allow glucose to react with some more reagents which otherwise shows reaction with open aldehyde, like here in glucose we saw it reacts with hydroxylamine and HCN to give you corresponding product, which is the characteristics reaction of carbonyl compound. Similarly, we have seen in aldehydes and ketone, carbonyl compound also react with 2,4-dinitrophenylhydrazine. They also react with sodium bisulfite. So we expected glucose to also react, rather open chain structure of glucose to also react with 2,4-dinitrophenylhydrazine. But no such reaction was observed when 2,4-dinitrophenylhydrazine was allowed to react with glucose. In fact, sodium bisulfite also does not give any addition product of sodium bisulfite when treated with glucose. So the first set of reaction which we have seen so far indicate that the open chain structure of glucose exists, but the second set of reagent somehow are not able to tell us that there is existence of open chain structure glucose. So question arises whether or not open chain structure of glucose exists. If does not exist, then in which form glucose exists? Hence, to understand this, the further research was done, and we then realized that glucose in nature, in maximum proportion, almost in all the proportion, glucose exists in a closed chain compound, that is cyclic chain compound. Now, how exactly the cyclic chain structure of glucose exists, we'll be seeing shortly, but in the next class. So today, guys, we'll have to stop here in the chapter of biomolecule, where we studied carbohydrates, and we have studied the introduction of biomolecule, introduction of carbohydrate, its old way of defining carbohydrate, modern concept of carbohydrate. We saw the entire D series of glucose. We saw what is the term called as epimers, how to remember their structures. We also saw how glucose can be prepared commercially as well as in the laboratory, and some important chemical reactions of open chain glucose which were ideally performed for the structural confirmation or the determination of a structure of glucose. But at the same time, we saw some of the reagents are not responding to the glucose, which indicates that the open chain glucose probably does not exist. Hence, that gave us idea of the glucose might be existing in a closed chain, which is then further experimentally proven. But how exactly the cyclic structure of glucose exists, we'll be seeing that in the next class. So that is it from our today's class. Guys, do revise this one and come prepare for the next class so that you understand in a better manner. We'll stop here today. Thank you so much, everyone.